Here's a do now based on what we did on Monday. So we'll go quickly through this. Most of you seem to do okay with it. So it says, what direction would the object move as it entered the magnetic field? So first things first, we have a positive particle, so we're going to use our right hand. So I hope everybody has their right hand up. The magnetic field is into the page, so I hope everybody's fingers are facing your page. The velocity is to the right, so now our thumb should be facing to the right of our screen. And with all that set up, our palm should be facing up. So here's what this would look like. Here's what the diagram would look like if we were in that magnetic field. The force would be upwards. The velocity would be to the right, at least initially. And the magnetic field is into the board. Okay, so hopefully at this point we've done enough of these. It's getting a little bit simpler for you. So now what we need to do is we need to talk about this. We need to talk about the magnitude or the strength of the force. So here's the formula. It looks a little bit more complicated than it is, so stick with me here. F is just the force, obviously. It's in newtons. The charge is Q, and it's in coulombs. The velocity, V, is in meters per second. Now, B, that's a new thing. That's the magnetic field strength. It's kind of like electric field strength, where it was just the strength of the field in a particular place in space. Okay? Now, it has its own funky name. It's called a Tesla, named after Nikola Tesla, who had a whole bunch to do with using magnetic fields to create electricity, all the electricity around us at this point. I think I made you guys watch a boring documentary at one point on that. And we use uppercase T to represent that. Now, the last piece, which is the part that, again, is slightly tricky, but nothing crazy, is this, theta. Theta is the angle between the velocity and the magnetic field. Okay. So what I've done here, let's ignore the writing up top, we'll get to that. What I've done here is I've tried to recreate in kind of a three-dimensional model what happened in the do now. So if you look at the do now, the velocity was to the right, so in the positive x direction. The force is in the positive y direction. And the magnetic field would be into the board, which is technically the negative z direction. So it's kind of going that way. So the picture here is trying to represent that. This is the positive x direction. This is the positive y direction. And this is into the board. Now, if we think of this as into the board, this guy here, then you could argue, and you can use your arms to prove this to yourself, if you face in front of you and you point in front of you as if it were into the board, and then you point your arm off to the right, your right arm off to the right, your arms are representing a vector into the board and a vector to the right of the board. And what is the angle between your arms? It's 90 degrees. Now, up here, it discusses a fun fact about that 90 degrees, which we're going to talk about now. So, if I want to find out the force acting on this, I would have to know some information about it. So I'm going to say the charge. Let's call the charge 2 coulombs. Let's say that the velocity is 200 meters per second. And the magnetic field strength is going to be 2 Tesla. Okay? So now we're going to calculate out the strength of the force acting on this guy. FB equals QB sine theta. FB equals the charge, which is 2 coulombs, the velocity, which is 200 meters per second, the magnetic field, which I said was 2 Tesla, sine 90 degrees, because that's the angle between the magnetic field and the velocity. Now, we know our basic trig, hopefully, and we know that the biggest that sine of an angle can be is 1, and that happens when it's sine of 90 degrees. So anything smaller than 90 degrees is going to give you some fraction of 1. So sine of 90 degrees is the biggest, which means in any other situation, oh, sorry, in any other situation, this number would be smaller than 1, which would make this number smaller. So when it's at 90 degrees, or when the force, or rather the velocity and the magnetic field are perpendicular to each other, the force is going to be at a maximum based on these other pieces of information. So it's the biggest it could be with a 2 Coulomb charge moving at 200 meters per second through a 2 Tesla magnetic field. And just for the sake of completeness, let's find out the value of it. So sine 90 is 1, so we don't have to worry about even writing it. 2 times 200 is 400, times 2 is 800. So our force will be 800 newtons. Now, the next scenario is a little bit weird too, because you would imagine that as long as you have a charge and you're moving through a magnetic field, you should feel a force, because magnetic fields are caused by moving charges. But this is really weird thing that's backed up by the mathematics behind it, which is if a particle is moving parallel to the magnetic field, which means the angle between the velocity and the magnetic field is either 0 degrees, so they're right on top of each other, or they're 180 degrees from each other. In both of those scenarios, if we go up here and look at this mathematically, if this is either 0 or 180, those of you who are good with trig right now saying, oh, that's crazy, because sine 0 and sine 180 are both 0. So it doesn't matter what any of these values are. The force that this object would feel if it was moving perfectly parallel, either in the same direction or exactly opposite direction, if it was moving in the same parallel plane as the magnetic field, it would feel no force. Okay, so those are the two basic scenarios where either it's moving at 90 degrees, perpendicular, perfectly perpendicular to, where it's maximum force. Now the good news is most of the time that's the type of question we're going to ask, and all the applications we're going to do next week are going to discuss, I wouldn't say all, but the vast majority of the applications we do next week are going to be talking about that idea. But every once in a while they give you one like this, where they're not exactly perpendicular or parallel. So let's go through this one real quick. It says in electrons. Now they didn't explicitly tell you the charge, but they implicitly gave it to you. And by now in this school year, you should know that one electron has 1 e of charge, which is 1.6 times 10 to the negative 19 coulombs. Okay, they then say the magnetic field is 5 Teslas. They say the velocity is 4,000 meters per second. And it then says the angle between the velocity and the magnetic field, so that's our theta, is 37 degrees. And they ask for the magnitude of the force, so we're just going to say FB is equal to QVB sine theta. FB is 1.6 times 10 to the negative 19 coulombs. V is 4,000 meters per second. B is 5 Tesla. Got sine 37 degrees. So we're going to go through and do our math. Should come out to be 1.92 rather, times 10 to negative 15 newtons. Okay. So I understand that this topic has been a little bit of a mental drain. It's the first time we're thinking three-dimensional. So the assignment I'm giving you isn't going to be a whole bunch of questions, but it is going to put together knowing the direction and knowing the magnitude. So it's going to put together Monday's lecture with this lecture, okay? But I wouldn't panic too much. What we're going to do on Friday is we're going to set this thing up where we're going to go over both assignments, okay? We're going to go through whichever ones you need to go through. We're going to make sure you get them. But then I'm going to have maybe 2 or 3 examples ready for us to go over. All right? As if we were in class. So I'm going to ask you guys, you're going to participate. We're going to actually have a real almost lesson. Yay. All right? So I really highly suggest, especially if you're having a hard time with this, please make sure you come to the Zoom call on Friday. You guys know your particular times, and it will hopefully we'll get a chance to make some of these things a little bit easier for you. All right? I will talk to you guys on Friday, and have a good rest of your week.